Welcome to the channel. Today we examine the nuclear propulsion system aboard the USS Gerald R. Ford, the flagship of the Navy's newest aircraft carrier class. This engineering marvel powers a 100,000-ton vessel for over 20 years without refueling, generating enough energy to sustain continuous operations worldwide. We will explore the design of the A-1B reactors, their role in daily ship functions, and the rigorous protocols that ensure safe and reliable performance. These details highlight the fusion of advanced science and human expertise that keeps the carrier at sea indefinitely. This channel is dedicated to military aviation and naval operations, with a focus on the technology and personnel that make them possible. If you appreciate in-depth looks at modern military hardware, please like the video and subscribe for more content. Let's begin. The USS Gerald R. Ford, commissioned in 2017, is the first of its class, designed to maintain U.S. naval dominance into the 21st century. Measuring over 1,000 feet in length and displacing more than 100,000 tons when fully loaded, it serves as a mobile airbase capable of deploying up to 75 aircraft. At the core of its endurance is the nuclear power plant, consisting of two A-1B reactors developed by Bechtel and Babcock and Wilcox. These reactors provide approximately 700 megawatts of thermal power, translating to about 250 megawatts electrical, enough to supply electricity to a city of 100,000 people while simultaneously driving the ship's 4 propeller shafts at speeds up to 30 knots. Nuclear propulsion on aircraft carriers dates back to the USS Enterprise in 1961, which used 8 smaller reactors. The Nimitz class, operational since the 1970s, relies on 2 A-4W reactors per ship, each producing around 550 megawatts thermal. The Ford's A-1B represents a generational leap. 25% more power from a more compact design, with improved efficiency and reduced crew requirements. This allows the carrier to operate without the logistical burden of fossil fuels, eliminating the need for frequent port calls for bunkering and enabling extended deployments of up to 3 years between overhauls. To understand the A-1B reactors, consider their fundamental operation. Each reactor uses enriched uranium fuel, typically uranium-235 pellets clad in zirconium alloy, arranged in fuel assemblies within a pressure vessel. Control rods of neutron-absorbing materials like boron regulate the fission chain reaction, where uranium atoms split to release heat and neutrons. This heat transfers to pressurized water in a primary coolant loop, which circulates through steam generators. The secondary loop produces steam at high pressure, over 1,000 degrees Fahrenheit and 1,000 psi, to drive turbines connected to generators and propulsion shafts. Unlike pressurized water reactors in commercial plants, the A-1B uses a once-through cycle optimized for marine use, minimizing space and weight. Safety is paramount in nuclear operations. The reactors are housed in heavily shielded compartments amidships with multiple barriers. The fuel cladding, reactor vessel, primary containment, and the ship's hull. Redundant cooling systems, including emergency core cooling and decay heat removal, prevent overheating even if primary pumps fail. The design incorporates passive safety features, such as natural circulation via gravity and convection, which activate without power. Navy standards exceed those of civilian nuclear facilities, with radiation levels monitored continuously to stay below 0.1 rem per year, far under occupational limits. A typical day for the nuclear engineering crew begins in the Reactor Control Division. The ship operates 24/7, with 3 watch sections rotating every 8 hours. Reactor operators, highly trained nuclear-trained sailors, monitor parameters like coolant temperature, pressure, and neutron flux via digital consoles in the control room. Adjustments are made in real time to match power demands, surging to full output for high-speed transits or throttling back during quiet periods. The crew, numbering about 150 nukes out of the ship's 4,500 personnel, includes machinists' mates, electricians, and electronics technicians who maintain auxiliary systems like pumps and valves. Power distribution is equally critical. The A-1B feeds a ship-wide electrical grid at 6,500 volts, stepped down to 450 volts for most equipment. This supports not only propulsion, delivering 260,000 shaft horsepower, but also advanced systems like the electromagnetic aircraft launch system, dual-band radars, and electromagnetic spectrum management tools. During flight operations, a single launch cycle draws power equivalent to a small town's peak demand. Yet the reactors respond seamlessly, maintaining stability without fluctuations that could disrupt avionics. Refueling occurs every 20 to 25 years, a process that takes about 3 years during a major overhaul. The Navy cuts into the reactor compartment, removes spent fuel assemblies, each containing about 100 pounds of uranium, and installs fresh ones. This interval is 3 times longer than diesel carriers of World War II, which refueled weekly. The fuel's high burnup, over 100,000 megawatt days per metric ton, means less waste and greater efficiency. Declassified reports indicate the Ford's reactors could theoretically run for 33 years before needing replacement, though the hull's lifespan limits service to 50 years. Crew life in the nuclear spaces reflects the demands of the technology. Qualifications take 2 years, 6 months of nuclear power school in Charleston, South Carolina, followed by prototype training in Ballston Spa, New York, where sailors operate full-scale reactor simulators. On board, the engineering spaces are warm and humid, with constant hums from pumps and fans. Daily rounds include leak checks, valve alignments, and chemistry tests on coolant samples to detect impurities. The work fosters a tight-knit community. Many nukes come from engineering backgrounds, and the job offers one of the Navy's highest re-enlistment bonuses due to its prestige and post-service opportunities in the energy sector. To illustrate real-world application, consider the Ford's 2023 deployment to the U.S. 6th Fleet, where it conducted operations amid heightened tensions in the Eastern Mediterranean. The reactors powered non-stop flight surges, generating over 10,000 sorties, while the ship steamed 50,000 nautical miles. In one high-intensity period, simulating contested seas, the power plant sustained 150 aircraft launches per day, including F-35C stealth fighters requiring precise electromagnetic catapults. Nukes adjusted reactor output to compensate for rolling seas, ensuring zero power dips that could abort missions. A post-deployment review praised the A-1B's 99.9% availability, with no unscheduled shutdowns. Maintenance routines prevent degradation. Weekly evolutions include turbine inspections via bore scopes and fuel handling drills. The crew uses predictive analytics software to forecast component wear, replacing parts like steam generator tubes proactively. This contrasts with older reactors, where corrosion led to more frequent interventions. The A-1B's modular design allows for in-situ repairs, minimizing downtime. As we reach the midpoint of this video, I encourage you to reflect on these operations. If you have experience with naval engineering, perhaps from service on nuclear-powered ships or familiarity with propulsion systems, please share in the comments. What challenges do you think define nuclear carrier life? Continuing, the A-1B's advantages extend to strategic flexibility. Without fuel constraints, the Ford can surge to any global hotspot, weather the South China Sea or Arctic routes without resupply vulnerabilities. This endurance supported the ship's role in multinational exercises like Baltic operations in 2024, where it integrated with Allied forces for weeks without logistical pauses. The reactors also enable hotel load operations, full electrical support in port for aircraft maintenance or humanitarian aid, powering desalination plants that produce 400,000 gallons of fresh water daily. Environmental considerations are integrated from the start. The Navy's nuclear program has operated without a reactor accident in over 60 years, with spent fuel stored securely at sites like the Portsmouth Naval Shipyard. Modern designs reduce radioactive waste by 30% compared to predecessors, aligning with sustainability goals. Looking ahead, the A-1B will power the Ford class through 2070 with upgrades like digital twins, virtual models for simulations, enhancing training. Future carriers may incorporate small modular reactors for even greater efficiency, but the A-1B sets the benchmark. In summary, the USS Gerald R. Ford's nuclear heart, powered by two A-1B reactors, delivers uninterrupted energy for over 20 years, fueling everything from catapults to radars without refueling. This system, backed by skilled crews and robust safety measures, ensures the carrier's role as an enduring projection of power. If this video provided useful insights, please like it and share with fellow military enthusiasts. In the comments, let me know. What aspect of carrier propulsion fascinates you most? Reactor design, crew routines, or strategic implications? Thank you for watching. I appreciate your time. Subscribe for more on military advancements, and I'll see you in the next video.